Okay, so welcome to the second week of Robot Systems Programming, Spring 2018. I'd like to give a big vote of thanks to Soham Pretkar and Tyler Payne, our super TAs, who have assembled a zillion EdgeMIP robot kits for you. Yay! We wanted to get the EdgeMIP kits out to you sooner rather than later, so that if you finished this week's programming assignment, you could swing right into working with the EdgeMIP. And I'll give you a little bit of a preview of next week's assignment. Next week's assignment is to get the EdgeMIP running and drive it around with a joystick. And I can demonstrate that in class. If you are working on your kit, if you find that you need you're missing a part or something, or you need an extra screw, then contact us, and we have extra ones.
Yeah, if you're missing a part,
yep.
we try to make sure every kit had every part, but please let us know when we have parts.
And did you put in extra of the half-inch number 4s?
Yep, we handed them out.
Great.
So
good.
Theoretically, you should have everything, but if you go through the instructions and you can't figure out if you're missing a part, please let us know.
And we'll be having office hours as usual. And if that doesn't work for you, then just contact us and we can meet you some additional time and help you out. You will have to solder 4 wires, so 2 wires each to 2 motors. And so the TAs and I will have soldering irons in the office hours. Or if you just swing by Krieger 70 sometime, if you don't have a soldering iron or laboratory available, if you swing by Krieger 70, which is the high bay laboratory over in Krieger with a big water tank, then my students will use the soldering irons there. It's a pretty easy job. Do you gentlemen have any comments on the kits?
Yeah, I'll just add, there are a few steps in the procedure where you have to actually physically modify parts. So you should not have to do that. I tried to go through and make sure every kit was modified. So you shouldn't have to drill anything or cut anything. It should just all be. So again, if that's not the case, please let us know.
Good. We'll take a quick look at the assembly instructions, and I'll point out those steps.
They should all be done already.
Good. All right. Any questions?
I know 2 students that were sick today and couldn't come. They're on hours. Do they get fees in the office hours?
No, they have to buy their own. No, just kidding. Yeah, if they just swing by in office hours, we'll give them the kits. No problem. Any other things that you guys want to mention to the class?
No, if you're going to go through these,
yep.
You're going to do that at the beginning. So
yep.
I might just hang out.
Okay.
If any comments come.
All right. Good. What we're going to do today is we'll mostly have a clinic where you can pull out your computer and work on this week's assignment, and I'll be available to answer any questions. And I believe that last time I covered all the things that we need to I previewed this week's assignment. This week's assignment, like every other assignment, is due next Tuesday before class. I mentioned last week that a couple of people were looking on the wrong web page. So here's my group's web page. I gave a short course last November up at the Woods Hole Oceanographic Institution, which consisted of 6 modules from the course that we're doing now. But these things are somewhat obsolete, so don't refer to that, please. Refer to the one at the top, which is Robot Systems Programming, Spring 2018. And I've updated that for all the latest stuff. So ROS launch, nodes, TF, parameters, that's what we want to do this week. And are there any questions? I think I covered that pretty completely in the last class. Then let me just preview for those of you who work ahead and want to get started on next week's assignment. I've updated the instructions here. And for next week's lab, many of you are going to build robots, and there are instructions here. There's a special page that I've put together. The first thing is to get your robot running, and that page is here. You can see it here. ROS on the EduMIP resource page is the page in question, and there's an introduction, a list of ingredients. You need to have a BeagleBone Blue or a BeagleBone Black with a robotics cape, and the ones that are pre-assembled are the latter. The ones that are you will be assembling, the ones for those who are assembling it, you'll be using a BeagleBone Blue, and the BeagleBone Blue is a design that takes the robotics, all the I/O of the robotics cape and the BeagleBone Black, and smushes them together into one board, which is pretty nice. And that board, in addition to containing an ARM processor, it contains a 9-axis IMU, a barometer, 4 quadrature encoder inputs, 4 H-bridge PWM outputs, 8 servo outputs for RC servos, and a whole bunch of serial and analog input and output. And it also contains a charge controller for this lithium-ion battery. You'll need an EduMIP kit, and you all have those. And that is all the plastic parts and the motors and things like that. You'll need a micro SD card, and the new ones I got are 16 gigabytes. The image that I posted for you is about an 8 gigabyte image. And there's 2 images that I posted. They're available here. And one of them is for the BeagleBone Black Wireless, and one is for the BeagleBone Blue. And the images are slightly different because the I/O ports for the hardware are slightly different on the 2 boards. But they're both Ubuntu 16.04. They were updated as of a week ago with apt-get update. And they have ROS pre-installed, and they have a Catkin workspace pre-installed with 2 basic packages for the EduMIP. And they also are set up so that if you power up the robot with this image, and this wireless access point is in, if it can see any wireless access points that you've given it the SSID and password, it'll automatically connect to them, so you don't have to log in with the USB cable and mess around with it. And the EduMIP instructions you can download here. I'll download it to my desktop. See, the rest of the ingredients are you need an image of Linux, and we're happily using Ubuntu 16.04, and it's a binary installation of ROS, just like you do on your desktop. And last but not least, a USB joystick. And the instructions. This is what Tyler was referring to. I last updated these things for the BeagleBone Blue. And it's kind of hilarious. If you look on the Strawson website, it was a bill of materials made by a computer scientist, and a lot of the things were wrong. This is a correct bill of materials. Your kit looks something like this, and this is the BeagleBone Black with the robotics cape, and that's been superseded now by a single board computer, the BeagleBone Blue, that has functionality of both boards all built into one. So these are the motors and the motor case. These are the connectors for the motors. The connectors for the motors have loose ends here, flying leads on this end, and a plug on this end to plug into the board. And so these are the 2 leads you're going to solder. And this 4-wire connector is for the encoders for the motors, which are connectorized. And so you're going to make these 4 solder joints on the motors with that little piece of wire. A word here. The connectors on these boards are really, really, really fine. If you look at the pins, they're like your hair. So when you mate the connector, make sure that the connector is parallel and square with the receptacle. You don't want to just kind of jam it in at an angle. with a wall socket connector like this for 110 volts, you can kind of jam it in and bang on it, and nothing bad happens. But for these little connectors, you'll bend the pins and possibly make the part a piece of junk. So notice how this is being inserted square to the receptacle, and you just translate it parallel. If you have any questions about the fine touch of manipulation, then ask the TAs, and they can give you a demonstration. So those are the encoder cables. In an earlier version of the EduMIP, you had to actually solder the encoder cables onto the board here. This is obsolete. Our boards are connectorized to this end. And assembling the EduMIP. And this is the assembly instructions for the BeagleBone Black, the older one. And this part of it, on page 10 begins the instructions for the BeagleBone Blue. And so I think I wrote this up in my parents' dining room over Thanksgiving. And too bad I didn't leave anything in there. And it says that you've got to do a little bit of destruction on the kit. Specifically that you have to drill a hole through this bumper here. It's this one, Tyler? Yep. You have to drill a hole through this bumper here. And those holes, Tyler and Solom already drilled the holes for you, so you don't have to do that. And you also have to break off a part that would have interfered with a component on the BeagleBone Blue, and that part has already been removed, so you don't have to do any destruction. The destruction's been done for you. And you can see here's the back of the board where they put it looks like an inductor here on the back of the board, and it obstructed that little tab. And this shows drilling out this hole with a 1-inch clearance, with a 1/8 inch bit, and Tyler and Solom have already done that for you. And this shows you for the BeagleBone Blue how I assembled mine, and it seemed like a decent way to assemble it. And notice, and you can see which direction the fastenings come. And another picture of the assembled. This is the assembled EduMIP showing. These are the motor wires that carry power to the motors, and these are the encoder wires, 2-wire motor wires, plus and minus. And these are the encoder wires, plus 5 volts, 0 volts, actually I think it's plus 3.3, 0 volts, and then channel A and channel B. And they need to be plugged in exactly in these positions for the thing to work properly. And this is a good shot of the BeagleBone Blue. You can see this is the Wi-Fi chipset USB port. The memory card is right in behind here, and this is the CPU and memory. This is all the extra I/O, motor connectors, encoder connectors, support for 8 servos, and so on and so forth, and the connection to the battery. Yeah. So, any thoughts, gentlemen?
So I would just say, if you find extra parts in your kit, sometimes there are like spare wires and stuff. Just keep all of those and give them to us TAs whenever you're finished. Someone we can save these for next year. The other thing is with memory cards, you're going to have to burn the image onto the memory card.
Oh, right.
Regardless of which version you have, you're going to have to do that. So even if you're already assembled, you're going to have to take the memory stick out. We have some card readers in.
Yep. So you can in the instructions here for assembling and testing the EduMIP, I've linked to some videos, and you want to download those instructions. A couple of cautions. Once you assemble your robot, if you're carrying it around in your backpack, carry it around inside the plastic container that's designed to protect the robot. And probably a smart idea when you power down your robot to disconnect the battery from the board. Just pull that little connector, which is right here where the battery plugs in. That way, if something shorts out a lead on the board, then it's not going to scorch the board because the battery is disconnected. And so and there's pretty detailed instructions here for testing your BeagleBone. You can, with no micro SD card installed, it will boot up over on a Debian image that's installed right on the board. There's a 4 gigabyte flash memory on board the BeagleBone, and So without flashing any micro SD cards, you can boot it up and see that the board is basically functional. And what you'll need to do to get the image that we need is go to this website, which is linked here, download one of these two images. It's an 8 gigabyte image that's been compressed, zip compressed to 2.5 gigabytes. You don't need to uncompress it. And so if I were to burn an image here, on my computer, I would get an adapter that has a, there we go, got an SD card adapter that takes a micro SD card inside of it and adapts it to the SD card slot in my computer. And when I put it in here, my computer will recognize this as a two-partition device. And if I want to reburn this micro SD card, I'll unmount both of the external partitions. And then I'll run Etcher. So I'll run the Etcher program, and I'll select the image that I want to burn. And so I'm going to select code BeagleBone Blue Ubuntu. So if I were going to burn for the BeagleBone Blue right here, I'll select this compressed image. I don't need to uncompress it because Etcher knows how to uncompress images on the fly. And then I'll select what I want to burn. I'm going to burn this 16 gigabyte micro SD card. And I press flash, and 10 minutes later, it will have burned the card, and then it'll read back the card and verify it. If you have any problems, let us know. If your computer doesn't have a SD or a micro SD slot on it, we've purchased 10 USB dongles that you can use to burn things. So if you're working with Apple hardware, you probably don't have a micro SD slot, but we can loan you a burner that you can use that you can just plug into your USB port. And then once you burn the image, you take it and you install it in the micro SD slot, which is located right here on the top of the people. So that's enough to be dangerous on next week's assignment, I think. So, Tyler, can you think of anything else?
You might have to format the SD card for the one who has you might have to format the SD card, right?
Nope.
No?
Nope. Etcher is just doing an image dump. It's like DD. And so that's why you need to unmount the micro SD card. If it's got a valid image on it, you want to unmount it. And Etcher does the equivalent of a DD. It's just writing bytes out to the hardware device. So Etcher doesn't even know about partition tables or anything like that. It just dumps. Tyler, anything?
Yeah, I can't think of anything else.
Okay. So we'll go through this in greater detail next week. But I wanted to just get you started. And if you have any questions, if you do go ahead, you're welcome to. And if you don't get to this until next week, you're okay. I just wanted to I know that some students have been making good progress in this week's assignment, so I wanted to get hardware in people's hands in case they were curious. Let's see. Questions, anyone? No, there's a place, this external charger, there's a place to plug it right in. And hand me the robot for a second. I'll actually use this one. This takes, I think it's from 9 to 16 volts, something like that. And these are 12-volt chargers you get. And when you plug them in, you get a bright green light, and when it's charging, it gives you this little sort of charging thing going on. When it's fully charged, then all the rest are green.
charge it, you use like chances and all.
Yep. And the first time you connect to it, you're going to connect to it by plugging a micro USB port into it. And so there's a micro USB to Type A USB adapter. And so example here. And so you're going to use this to connect to it for the first time, following the instructions. And I'll go through that in greater detail next week. If you have any instructions for us, we'll go through the whole thing in chapter and verse next week. And where I want you to get to by the end of next week is I'd like you to be able to do, at a minimum, this. So this is the goal for next week. You have a working robot, and you can I always write the and when you bring your robot up, when you bring it to class, we can set you up so that it will be allocated the same IP address each time, but you need to have your robot running for us to do that. This one is always allocated to 104, and I can SSH to it, and there it is. I'm SSH into it.
We also need to make sure that we don't put the 12 volt connection in the 5 volt.
Yes, good point. For those of you who have pre-built robots, take it out, take a look at it, and you notice that it's got two boards and it's got two charging ports. One of them has a plug in it, a little blue plug, and the one on top in the middle has no plug. This is a 5-volt port for charging the Beagle Bone Black. If you plug your 12-volt adapter into it, then the smoke will rise out of the board of working light. So that's why these Beagle Bone Blacks have a little blue plug in one of the charging ports. So always use the outboard charging port. So see a little blue plug right there? So yeah, and I 6 to 16 volts is what it takes. And in the instructions, I have tried to warn you about that. Right here. If you're using the Beagle Bone Black and robotic tape, don't cross the 5 volt and 9 volt streams. Bad things will happen. All right. So, so where I want you to get to is you can log into the machine, and the password for you're going to log in as Ubuntu, and the password is temp pwd. You can see it actually tells you what the password is. Very secure system. And in the message of the day, I put up some information on on where this image came from and who contributed to it. Several people did, to whom I'm grateful. And then you can do things like HTOP. You can see what's going on with the CPU. You can see that this machine has a half a gig of RAM, and it's got a 1 gigabyte swap file, and it's got a single core. And we can do ROS launch. You're going to do some other things, initializing the board and calibrating the gyros and things like that are in the instructions. And we'll go over that in greater detail, but it's all on the course webpage. And so I'm running a program now that is going to cause the robot to run its balance program. And when I pick it up, it'll think about it for a minute, and it'll start balancing. And then on my host, my PC over here, oops, hang on a second. I just Control C. I want to start here. Twist. On my host, I'm going to start a program called Joy Twist, and notice I'm logged into that machine over there. And if I set my environment variables properly, Sorry, give me a second. I just need to set some environment variables. That's right. Okay, so I've got a joystick process running, and the joystick process is publishing on the topic joy, and we looked at this echo joy, and the standard joystick process publishes messages when I move the joystick, and you're going to write a node which reads that, and it publishes a twist message, edge emit command, and it publishes it at 10 hertz, and there it is. And both of these windows are on my PC. When I SSH into .104, you're going to cover next week we'll set the environment variables, so now I'm logged into that machine, and I should be able to say ROS topic list, and it should think about it, but it should eventually give me the topics. Environment variables are wrong, sorry. We're on the 10 subnet. All right, when you set your environments environment variables properly, then on that machine is accessing the ROS core here, and I can say ROS topic echo edge emit command, and on that machine over there, and you can see that it's getting the messages that are being transmitted from the process here to the process there via Wi-Fi. And so if we run the balance program subscribes to a topic called edge emit command, and it balances. And so when I press my joystick, since it's subscribed to those messages, it's going to respond. And if I pop up another window here, and I say ROS topic list, this is a local window. You can see that there's an edge emit state message being published, and we looked at this in the first day of class, but now that you know about topics, everything there is to know about topics, I can say ROS topic echo edge emit state, and we looked at the state message. You can see that it's publishing the entire state of the robot, including the battery voltage. A fully charged battery is about 8.4 to 8.5 volts, and a fully discharged battery is around 7.5 or 7.6, just FYI. But it gives the duty cycle of the PWMs, the angles of the wheels and radians, and it integrates the wheel velocity odometry and it computes the northing and easting of the vehicle. It's a pretty dumb program right now. It assumes that when it wakes up, it's pointing north, so it's not actually using the magnetometer. So if somebody wants to improve upon that, then that'd be great. And RQT graph. And if we look at RQT graph for this, now that you know everything there is to know about topics, you can see this is the joystick node that's provided by Ross. I didn't write it. It publishes joy messages. This is the thing that you write. That you write. Joy twist. It publishes a twist command. I called mine a different name, but it's the joy twist that you're responsible for. And then the edgemint Ross balance node is running over there, and it's publishing edgemint state. And my Ross topic echo is subscribing to it. So that's the data flow. Any questions? Okay. So that's kind of a quick overview. We'll do that. Do it again in greater detail on Tuesday. Tyler, Soham, anything? Any questions on this week's assignment? Yes.
So when you press forward, is it constant acceleration or
Velocity.
constant?
Yep. Yep. Velocity. And so it's running closed loop. It's running closed loop on heading, closed loop on body tilt, and closed loop on heading rate and forward velocity.
That's something you can change.
Yep. Yeah, and you have the source code on in that image, and it's on a Git repo that's accessible to you, and so you can hack it and you can recompile it. And I'll demo in greater detail next week. Okay. So the rest of this class, for anybody who wants to stick around to work on this week's assignment, I'll be available. I did say that I'd have a robot of the day to introduce you to. And so I'm going to actually introduce you to several different robots that were developed at a company called Boston Dynamics. And my friend and graduate school office mate, Al Rizzi, is their chief engineer. And the guy that founded Boston Dynamics is a fellow by the name of Mark Raybert. And Raybert was an MIT faculty member and was rather famous in the 1980s for building a series of robots that balanced and hopped. And we didn't really know how to make robots that walked, but it turns out that hopping is in some ways easier than walking. And Mark Raybert was the first guy to figure that out. And he wrote a book in the 1980s called Legged Robots That Balance, which is a real classic. And he got interested in doing more and more practical things with legged robots and decided to start his own company. And he did that with Boston Dynamics. And they built a whole series of legged robots. And this is one from about maybe 8 years ago, 10 years ago almost. I'm sorry, 9 years ago. So it's published on March 7th, 2008, so 9 years ago. And so I'm going to show you several other robots that are more recent. This is a robot called Big Dawg. It was developed under contract for DARPA, and they wanted Boston Dynamics to build a robot that they could be used in the battlefield to haul stuff around, haul around ammunition, people, food, whatever, in terrain. And it was hydraulically actuated, and it's got a big an HPU, a big 2-cycle motor. It's like a 30 horsepower 2-stroke motor, and it makes a kind of a really strange sound. But that strange high-pitched sound is the motor that runs the hydraulic unit. So that's what it really sounded like. I don't have great audio capabilities yet. So a gasoline engine powered. Looks kind of creepy because it's a little bit anthropomorphic. And the packs on it are not part of the robot. That's the payload that the Big Dawg is carrying. It's called Big Dawg. And they found that it could negotiate a lot of different terrain. And one of the things they worked on was having automatic foot placement algorithms so that you could just basically say, go this direction, and it would figure out when it needs to, it would control its gait. And also, based upon how fast it was going in the terrain, it would change different gaits. So it would be a four-legged gait, or and faster, it would, for example, horses have about, I don't know, like 6 different gaits that are commonly used. The simple ones have all 4 feet on the ground, and the faster ones typically have 2 feet off the ground at any one time, like when you're running. And so this was 10 years ago the state of the art, and considered to be extraordinary. The robot was generally capable of righting itself when it fell down. Not always. If it was on its back, then it was stuck.
Uses the knees too.
Yep. So you can see this is a demonstration of different gaits. And you can see in this gait, not all 4 feet are on the ground at the same time. So there's a human controlling this only insofar as the joystick, it's like joystick forward and joystick back. The human is not controlling the details of the reflexes or where the foot placement is. It's a pronking gait, it's called pronking. So it's Boston Dynamics. Now, every good strange-looking robot, I think, deserves a.
I need to say 2 things that won't make sense to you. First,
Deserves a good spoof video. So this showed up on the internet not long after the big Dawg video showed up. Sorry about the resolution, it's the highest resolution I could find. Yeah, it's the HD version, yeah. So in LCSR, not every year, but some years, there's a Halloween sort of potluck get-together. And 4 or 5 years ago, when there was one of these Halloween get-togethers in the Robotorium, 2 students came as Big Dawg. It was hilarious. It was pretty hilarious. VHS cassette. That really gets it. Okay. All right. Any questions? All right, those of you who have your computers, if you want to work on things, I'll stick around.
Write anything on your computer,
and,
you need to get Grammarly.
That's the end of the formal program for today's class. Thanks, everybody.